Determinants were first used to determine if a system of linear equations had a unique solution. This idea was introduced in the Chinese math textbook, The 9 Chapters on the Mathematical Arts. Cardano writes about a 2-by-2 determinant rule similar to Cramer's rule around the year 1545. About a century later, Leibniz worked with larger determinants. Maclaurin proved Cramer's rule by the results of determinants. Cramer gives a general rule for n-by-n system of linear equations in his paper called Introduction into the Analysis of Algebraic Curves. Gauss introduced the term determinant, but Cauchy used determinant in the modern sense 11 years later. Determinants only exist when using a square matrix of n-by-n order. If the determinant is 0, the matrix is invertible or singular. The determinant of a 1-by-1 matrix is itself. Cofactors are used to find determinants of larger matrices. This creates a checkerboard effect. To find a 2-by-2 determinant, expand along a row or column. After expanding along the first row, this gives us AD minus BC. To find a 3-by-3 determinant, expand along a row or column. Let's expand along the first row. A times the determinant of the remaining numbers minus B times the determinant of the remaining numbers plus C times the determinant of the remaining numbers will give you the determinant of matrix B. This method can be used to find determinants of larger matrices. Another way to find a 3-by-3 determinant is to copy the first and second column to the right of the determinant. Starting with A, multiply the diagonals and add the product. Then starting with G, multiply the diagonals and add the products. Subtract the two numbers and the result is the determinant. For simplicity, the properties are proven with 2-by-2 or 3-by-3 matrices. However, these properties work for n-by-n matrices. Determinants of a transposed matrix is the same as the original. Assume matrix A is the following. Then its transpose is. Find the determinant of both matrices. By the commutative property of real numbers, the determinants are the same. Cauchy-Binet theorem. Determinant of the product AB equals the determinant of A times the determinant of B. Find the determinants of A, B, and the product AB. Multiply the determinant of A and the determinant of B. To prove this, take the determinant of A times B, multiply it out, combine like terms, factor, and the result is the determinant of A times the determinant of B. If two rows are interchanged in a matrix to form another, their determinants will be opposite of each other. Take the determinant of A and factor out a -1. The result will be the opposite of the determinant of B. If one row is multiplied by a scalar to form another matrix, the determinant of the new matrix equals the scalar times the determinant of the original matrix. To show this, take the determinant of A, multiply it by the scalar, and the result is the determinant of B. If a matrix is multiplied by a scalar, the result is the scalar to the nth power times the determinant of the original matrix. To prove this, take the determinant of the scaled matrix, Factor out x to the third, and the result is x to the third times the determinant of A. If a matrix has a row or column of all zeros, the determinant is 0. By expanding along the row or column of zeros, we see that the determinant is 0. If a matrix is triangular, then the determinant is the product of the diagonal. If two matrices differ by one column, and those columns are added to make a new matrix, the sum of the two determinants equal the determinant of the new matrix. When we add the determinant of A and the determinant of B, we will get the determinant of C when we factor. We can find an area of a triangle with given vertices. The area equals positive or negative 1/2 times the determinant. The positive and negative eliminates the use of absolute value bars. Here is an example. The determinant of our given points is 60. Since it's positive, we will multiply by positive 1/2, thus giving us the result of 30 units. We can use the same formula as before. If the determinant is 0, then 3 points are collinear. For example, take 3 points. Find the determinant. This determinant is 0, so these 3 points are in fact collinear. We can use determinants when solving system of linear equations. This is also called Cramer's rule. Find the determinant of the coefficients. Label this D. Then replace the x column with the constants and find the determinant. This will be dx. Do the same with y and z. To find x, y, and z, divide each of those determinants by the coefficient determinant. We can find eigenvalues and eigenvectors. We need to find the determinant of A minus lambda times the identity matrix. When we do so, we get the following. Solve for lambda. These will be your eigenvalues. Assume lambda equals RST. We need to find the kernel of the matrix when R is substituted. Use the reduced row echelon form and find its span. Repeat this for the other eigenvalues. Here is an example from Dr. Huffman's class. Find the determinant of A minus lambda I. Solve for lambda. One result is rational. When we find the kernel of the matrix when we substitute this real value in, we can find its span. This span is the eigenvector or eigenspace. In conclusion, determinants have properties just as real numbers have their properties. Also, there are many uses for determinants.